the ideas of binding energy and then go on to have a look at how this is relevant to decay and further nuclear reactions. We've seen this graph before. This is our graph of our binding energy versus the number of nucleons in the nucleus. That's the number of protons and neutrons. Okay. Let's just quickly check our definitions of things. Firstly, our binding energy is defined as the work that we need to do in order to split apart a nucleus. In other words, it's the energy required to separate a nucleus into its constituent parts. If you like, the nucleus is the cake and the nucleons are the ingredients, and we're thinking about the work we would need to do in order to do that. Now, obviously, it's not really fair to compare nuclei because they've got different sizes, so what we plot is the average binding energy, which is the binding energy per nucleon. And again, it's similarly defined. It's just the energy required in order to remove one of those nucleons. You can see there that we've got different values. For example, hydrogen, deuterium, hydrogen-2, it's a very low amount of energy required, whereas something like iron, copper, very high amounts of energy. Put very simply, the higher the binding energy per nucleon, the more stable the atom. What this means is it's harder for me to pull, for example, iron 56 apart than it is to pull hydrogen-2, helium-3, etc. Okay, so what we're going to do now is, now we sort of covered these very basic bits, I want to reframe the discussion, because actually this graph that we plot is kind of technically wrong. What's being plotted here is the average of the magnitudes of the energy. I'm going to just show you the real form of the graph, and what you'll notice is that actually when we're plotting binding energy, we should, okay, if we were going a bit beyond the IB or A-level spec, we should really plot it as a negative value. And this is because those of you who understand about potential energies, potential is a negative quantity. And really, when we're putting in energy, we are going to separate those particles out. They will have infinite distance, and at infinite distance, they'll have zero energy. So if we put in an energy, their initial energy must be less than zero. Don't worry about this so much. When you do an exam, you'll see the graph which is on the left. However, in order to understand what happens next, I think the one on the right is quite illustrative. Okay, so we'll just, for now, look at the picture on the right-hand side. Okay, actually, binding energy technically decreases. It becomes more negative as a nucleus becomes more stable. Now, this is where I have to fire a kind of exam klaxon. Okay, when in your exam you are writing about this, you can say that binding energy increases. However, what we mean there is the magnitude of the binding energy increases, but the binding energy itself actually decreases. It becomes more negative. And we could use ideas, for example, of a potential well. You're going further into the potential well. Okay, why is this important? Well, if the energy decreases, then energy must be released. And what this is released in the form of is in the form of kinetic energy of a decay particle, for example. We'll see that in a second. The result of this is that the mass of the daughter nuclei in any situation, as we become more stable, is going to be less than that of the parent nuclei. Any reaction is going to try and make us more stable. Okay, so this could be alpha decay, this could be beta decay, and the result of that is that the daughters, the products, is going to be less than that of the masses there are going to be less. Okay, so let's take an example. What's the energy released when plutonium-239 decays to uranium-235? Well, what we've got here is our plutonium-239 and our uranium-235 and our helium-4, which is an alpha particle. Okay, what we'll do here is we'll look at the masses in each case. We've got plutonium. I've looked these up. Okay, don't worry, you would be given these. We're given 239, 0.052157, etc., etc. Okay, high level of precision here, and we'll talk about why. Here we're in a second. Here we're expressing mass in terms of U, where U I'm using is 1.67 times 10 to the minus 27. I would go off and check that in your data booklet if you were doing this in the exam. What we want to do is think about the energy release. Well, what you can hopefully see is that if we calculate the total masses on each side, that the mass has decreased. In other words, my plutonium has decayed into two more stable things. Okay, uranium-235 and helium-4, both of which, if we go back to that graph, are more stable. Okay, what we're going to use is our equation delta E equal to delta mc squared, where delta m is our mass defect. Now you can see the numbers there, pretty disgusting. I'm pretty sure I've made a mistake somewhere, okay, because of that high level of precision. And we end up with a delta m, which is 0.005631 U. What remains then is to multiply that U by C squared in order to turn this into an equation. Okay, so we've got our mass defect in terms of U, we've got the value of U in kilograms, and then we've got 3 times 10 to the 8, which is C, and that's squared. And it produces a value of 8.46 times 10 to the minus 13 joules. Very small, but remember this is just the energy released with one decay, and typically when we've got our radioactive decay, this would produce a lot of decays and therefore a lot of energy. Small point, I've converted my units here into mega electron volts, so why not take the time, just have a second to compare your values to mine and see if those work out, and please do let me know if I've made any mistakes. Okay, this is for alpha decay. All right, and this is one process by which energy can be released. What we are interested in today is other processes whereby energy is released, and these are two you may have heard of. First one there on the left-hand side is nuclear fission, which is where a neutron is fired at, say, for example, uranium-235 to make it uranium-236, and it then decays into other products, in this case barium-144, some neutrons, and krypton-89. Now, the process here is very similar to our alpha decay, in that if we were to take the mass of the parent nuclei and then compare it with the daughters, we would find a mass defect and therefore a release of energy, and that's what powers our nuclear fission power station. So in this case, we're going from a big nucleus into a small one. Probably more sort of challenging is nuclear fusion. Now again, nuclear fusion, what we're doing there is we are fusing together two light nuclei to produce an unstable, slightly heavier nucleus, which then becomes more stable as a result of a decay. Okay, and again, if we were to take the mass of those parent nuclei and compare it to the daughters, we would find a mass defect and therefore an energy decrease. Now you should be aware that nuclear fission is a process in most of our power stations. Nuclear fusion is a process which is in the sun, and really, if we could replicate nuclear fusion on Earth, then we would find that we would be releasing a lot more energy, and therefore this would be a much more efficient way of producing energy. However, the reason we can't do so is because you need to do this at high temperatures. Okay, now the math still holds. We need to use our delta E equal to delta mc squared, and that's what I'm going to be looking for you guys to do in today's lesson. Good luck.